Today's topic is synchronous counters. We have studied ripple counter. This is the circuit for ripple counter. We have 4 JK flip-flops, and in this diagram these are negative edge triggered JK flip-flops. This is the LSB, least significant bit flip-flop, having output Q0 and inputs J0, K0 are connected to high. This output Q0 will toggle when negative clock edge arrives, and this output Q0 is connected to the clock of the next flip-flop and so on. This output Q0 will take some time to change its state, and if it is TP, propagation delay time, then if we use 4 JK flip-flops in this way, then total propagation delay time will becomes 4 times TP. TP is propagation delay time for one flip-flop. So if we use 4 flip-flops in this way, then total propagation delay time will becomes 4 times TP. And if we use n such flip-flops, then total propagation delay time will become n times TP. When the carry has to propagate through a chain of n flip-flops, the overall propagation delay time is n times TP. TP is of the order of 10 nanosecond. It is the propagation delay time per flip-flop. So if for each flip-flop we have propagation delay time TP, which is of the order of 10 nanoseconds, it is the time which the output of a flip-flop take to change its state when the inputs are changed. Then if we use n flip-flops, this overall propagation delay times become n times TP. For this reason, ripple counters are too slow for some applications. When propagation delay time is large, this device will be more slow. So ripple counters are too slow for some applications. In synchronous counter, clock pulses drive all flip-flops in parallel, by which this ripple delay problem is resolved. So in synchronous counter, clock pulses drive all flip-flops in parallel, and in this way the ripple delay problem is resolved. This is the circuit diagram of synchronous counter. Now we see that this clock signal drives all the 4 JK flip-flops simultaneously. In ripple counter, this clock signal drives LSB flip-flop only, and output of its, that is Q0, will drive the clock of next JK flip-flop and so on. But now in synchronous counter, this clock pulse will drive all the 4 JK flip-flops simultaneously. This clock is applied to all the JK flip-flops. Now these 4 JK flip-flops are positive edge triggered in this circuit diagram because of this triangle signal, and if we use a bubble with this triangle, then it will become negative edge triggered JK flip-flop. So in this circuit we are using positive edge triggered JK flip-flops, and this clock pulse drive all these 4 JK flip-flops simultaneously. With this, we have this CLR bar signal. This CLR bar signal, CLR means clear. This CLR bar signal, this also applied to all 4 JK flip-flops, and the bubble symbol indicate that it is low active. It means that if it is low, CLR bar is low, then it will be active and do its function. Its function is to clear. To clear means the output Q0, Q1, Q2, Q3 all will be 0. Outputs Q0, Q1, Q2, Q3 all becomes 0 if this CLR bar is low. It is low active. It is indicated by this bubble. Bubble symbol indicate that it is low active. Means CLR bar is low. It will be active and do its work of clear. Clear means Q0 is 0, Q1 is 0, Q2 is 0, Q3 is 0. So the output word Q3, Q2, Q1, Q0 will become 0, 0, 0, 0 when CLR bar is 0. We write here CLR bar in place of CLR. Because CLR bar is 0, it means CLR is 1. And it will do the function of clear. With this, we see that inputs J0 and K0 are connected to high, that is 1. In the ripple counter, all the inputs J and K of all 4 flip-flops are connected to high. But now J0, K0 are connected to high and J1, K1 are connected in this way to Q0, and the AND gate as shown in this figure. Similarly, J2, K2 and J3, K3 are connected with these AND gates. This is the circuit diagram of synchronous counter. Figure A shows synchronous counter with positive edge triggered JK flip-flops. Clock pulses drive all flip-flops in parallel. Because of the simultaneous clocking, the correct binary word appears after one propagation delay time rather than 4. J and K inputs of the least significant flip-flop are tied to a high voltage. J0, K0 are connected to high. So it responds to each positive clock edge. When positive clock edge arrives, it will toggle. Output Q0 will be toggle. The remaining flops can respond to the positive clock edge only under certain conditions. The Q1 flip-flop toggles on the positive clock edge only when Q0 is 1. When Q0 is 1, then the next flip-flop having output Q1, it will toggle. This Q1 will toggle only when Q0 is 1. When Q0 is 1, J1, K1 are 1 and Q1 will be toggle. Similarly, in next JK flip-flop, Q2 will be toggle when Q1 is 1. And Q0 is 1 also. Q1 will toggle when Q0 is 1 because J1, K1 are connected to Q0. And if Q0 is 1, J1, K1 are 1, Q1 will toggle. Now Q2 will toggle when J2, K2 are 1 and J2, K2 will be 1 only when Q1 is 1 and Q0 is 1 because the output of this AND gate which goes to J2, K2, this AND gate have inputs Q1 and Q0. So J2, K2 will be high only when Q1 is high and Q0 is high. Similarly, the Q3 will be toggle when J3, K3 are high and J3, K3 are high when Q2 is 1 and Q3 is 1 and Q1 is 1 and Q0 is 1. Q3 will toggle when J3, K3 are 1, J3, K3 are 1 when Q2 is 1, Q1 is 1 and Q0 is 1. These two AND gates are connected in such way that each flip-flop will toggle when the output of its previous flip-flops, all the previous flip-flops are 1. The Q1 flip-flop toggles on the positive clock edge only when Q0 is 1 The Q2 flip-flop toggles on the positive clock edge only when Q1 and Q0 are 1s, and the Q3 flip-flop toggles on the positive clock edge only when Q2, Q1 and Q0 are 1s. In other words, a flip-flop toggles on the next positive clock edge if all lower bits are 1s. A low CLR bar resets the counter to Q equal to 0, 0, 0, 0. It is low active CLR bar. So when CLR bar is low, it will clear and output word Q becomes 0, 0, 0, 0. When CLR bar goes high, the counter is ready to go. The first positive clock edge sets Q0 to get the word Q equal to 0, 0, 0, 1. Since Q0 is now 1, Q1 flip-flop is conditioned to toggle on the next positive clock edge. When second positive clock edge arrives, Q1 and Q0 simultaneously toggle and the output word becomes Q equal to 0, 0, 1, 0. The third positive clock edge advances the count by 1 and Q becomes 0, 0, 1, 1. Now since Q0 and Q1 both are 1, so Q2 will now be toggle, and the next positive clock edge will give Q equal to 0, 1, 0, 0. When we have Q1 is 0, Q0 is 0, word is 0, 0, 1, 1. Now Q1 is 1 and Q0 is 1. So next positive clock edge with Q3, with Q2, Q1 and Q0 also toggle, and the next word is 0, 1, 0, 0. Q2, Q1, Q0, all three will toggle. Successive Q words are these, so on up to 1, 1, 1, 1, equivalent to decimal 15. The next positive clock edge resets the counter and the cycle repeats. The advantage of synchronous counter is its speed. It takes only one propagation delay time for the correct binary count to appear after the clock edge hits. The controlled synchronous counter is shown in figure B. This is the circuit diagram for controlled synchronous counter. This was the circuit diagram of synchronous counter. J0 and K0 are connected to high. Now J0 and K0 are connected to a control signal that we write count. It may be high or low. When it is high, when count is high, it will work as this circuit of synchronous counter, and when this is low, then all flip-flops are inactive and it will not work. So the circuit will do work of counting when count is 1, and if count is 0, it will not work. Here we use 3 AND gates as shown here. In the previous case we have only 2 AND gates. Now here we use 3 AND gates. One count signal goes to all 3 AND gates. Next counter is ring counter. Instead of counting with binary numbers, a ring counter uses words that have only a single high bit. This is the circuit diagram of ring counter. This have only a single high bit. There are 4 bits Q3, Q2, Q1 and Q0, and we will get only a single high bit. In this circuit, we are using 4D flip-flops in this way. Clock signal is applied simultaneously to all 4D flip-flops, and these 4D flip-flops are positive edge triggered D flip-flops as shown by this triangle symbol. A control signal CLR bar, clear bar. CLR bar means clear bar. It is used in this way. In the LSB flip-flop, least significant bit flip-flop, this CLR bar is connected to PR. PR is preset, and the bubble shown with this PR shows that it is low active. So when CLR bar is low, it will active this PR preset, and the function of this preset is to make Q0 1. Preset means output Q0 is 1, and this happened when PR is low, because this bubble shows that it is low active, and it is connected to CLR bar. When CLR bar is low, PR is low, and output Q0 will becomes 1. This output Q0 is connected to D1, output Q1 is connected to D2, Q2 is connected to D3, and Q3 is connected to D0 in this way. And this CLR bar is connected to other 3 edge triggered D flip-flops in this way. These are all low active, and when CLR bar is 0, this will do the function of clear, and Q1, Q2, Q3 all 3 becomes 0. So when CLR bar is 0, what will it do? It do Q0 equal to 1 due to this PR function, and all other outputs bits Q1, Q2, Q3 becomes 0. So the word becomes Q equal to 0, 0, 0, 1. Figure A shows a ring counter built with D flip-flops. The Q0 output sets up the D1 input. The Q1 output sets up the D2 input, and so on. Therefore, a ring counter resembles a shift left register because the bits are shifted left 1 position per positive clock edge. The difference is that the final output is feedback to D0 input. This kind of action is called the rotate left. When CLR bar goes low, then back to high, the initial output word is Q equal to 0, 0, 0, 1. The first positive clock edge shifts the MSB into the LSB position. The other bits shift left one position, therefore the output word becomes Q equal to 0010. So initially when CLR bar goes low and then high, the initial word is 0001. We have 1 in LSB D flip-flop. When first positive clock edge arrives, it shifts the MSB into LSB position. Because this is the MSB flip-flop. Output of it is Q3 and it is connected to D0, the input of the LSB flip-flop. So since Q3 is 0, D0 is also 0, and for next positive clock edge Q0, which is initially 1, now becomes 0 because D0 is 0. So Q0 becomes 0 and Q0, which is initially 0, now initially 1, Q0 was initially 1, so D1 will become 1, and at next positive clock edge this Q1 will become 1, and we have this word 0010. So this high bit 1 is shift towards left. When next positive clock edge arrives, this one shifts one more position to the left, and the successive words are these. One is shifting towards left, one position for each positive clock edge. After the fourth positive clock edge, the output word is 0001. After 1000, we get 0001. Now this one goes to the from MSB to LSB. The stored 1 bit follows a circular path moving left through the flip-flops until the final flip-flops send it back to first flip-flop. This is why the circuit is called the ring counter. By adding more flip-flops, we can build a ring counter of any length. With 6 flip-flops, we get 6-bit ring counter, and successive ring words will be these. If we use 6D flip-flops, initial word is 000001, which is equivalent to 0. Next word, in next word, this 1 bit is shift towards left. This is equivalent to 1. In next word, this 1 bit again shift towards left. This is equivalent to 2, and so on. If a ring counter has n flip-flops, final ring word represent decimal n minus 1. Here, when we have 6 D flip-flops, the final word is 5. Applications of ring counter. Ring counters are useful when it is necessary to control a sequence of operations. Because each ring word has only one high bit, we can activate one of several devices. Consider 6 digital circuits A to F. These are 6 digital circuits from A to F, A, B, C, D, E, F, that can be turned on by a high Q bit. When CLR bar goes low, then back to high, the initial output word is Q equal to 0001. Q0 goes high and activate device A. In initial word we have high bit 1 to LSB, that is Q0. So initial word we have Q0 is 1 and other Q bits are 0. So this high Q0 will activate the device A. In next word this one shifts to Q1. Q1 become 1, others are 0. So it will activate the device B. In next word this one shifts to Q2. Q2 becomes 1, others are 0. So it will activate the device C. In this way, for next positive clock edge, the devices A, B, C, D, E, F are turned on successively. Successive clock pulses turn on each device for a short time. As a stored 1 bit shifts left, it turns B to F in sequence. This is the application of ring counter. Here we have clock pulse and CLR bar. CLR bar is low active due to this bubble sign. So initially when CLR bar is 0, this do the function of clear. Q5, Q4, Q3, Q2, Q1, Q0 all are 0. And when this CLR bar goes to 1, from 0 to 1, then next positive clock edge we get Q01, other Qs are 0. It will activate A, and in next positive clock edge it will activate B because then Q1 is 1, and so on.